Okay, we saw that there was a huge drawback when we try to find the interpolating polynomial with the original method. So we need a better technique to find the interpolating polynomial. To this end, we need a concept that we called it Lagrange polynomials. And after that, we will introduce the Lagrange interpolating polynomial. Let me consider 2 points, x0 and x1. Okay? For these 2 points, we define two, in fact, linear polynomial. We call them L0 and L1. We construct L0, okay, by writing x minus x1 over x0 minus x1. And also we define L1 to form x minus x0 over x1 minus x0. Now, if we define a linear polynomial, we call it p of x, to this form, L0x fx01 plus L1x times f of x1. This is the Lagrange interpolating polynomial of degree 1, and L0 and L1 are Lagrange polynomials. We have the table like this: xi and yi, x0, y0, x1, y1. Okay, and compute p of x0. Here we will have L0 x0 times f x0 plus L1 x0 times f1 x1. Okay, if you put x0 in L1, you will get that this term will be 0, so all of these vanish. And here, if you put x0 in this polynomial, you will get this one equal to 1, and this is f of x1, and this is y0. So you can see that p of x0 is y0. In the same way, we will get p of x1 equal to y1. So p of x that we defined in this form satisfies in the definition of the polynomial. So p of x is the unique linear polynomial passing through x0, fx0, and x1 and fx1. This is the idea of the Lagrange interpolating polynomial. Okay, now we want to extend this concept for n plus 1 nodal points, and we try to define Lagrange polynomial of degree n, and also we try to construct the Lagrange interpolating polynomial. First of all, we try to define Lagrange polynomial of degree n. We have n plus 1 nodal point. We call this nodal point x0 f of x0, x1 f of x1, x2 f of x2, and finally xn f of xn. We want to construct a polynomial passing through these points. Okay, first of all, we define lnk of x. This is in fact the Lagrange polynomial of degree n, okay, of degree n for the nodal point number xk. Okay, we define in fact the Lagrange polynomial lnk in this form. This pi means the multiplication of this fraction for different I from 0 to n. Just we have to note that I cannot be equal to k. So ln of k of x equal to pi I equal to 0 to n, and I is not equal to k, x minus xi over xk minus xi. If we extend this pi, you can find that if you put I equal to 0, you will get x minus x0 over xk minus x0 times x minus x1 over xk minus x1, and this continues until we arrive to x minus xk minus 1 over xk minus 1, and we jump over xk, because if you put xi equal to xk, so you will have a 0 in the denominator of this fraction, and it's not good. Okay, so we jump from k, and we get, and we will have the next term x minus xk plus 1 over xk minus xk plus 1, and we continue until the final point x minus xn. It will be, it's not true, it should be n over xk minus xn. This polynomial has a very interesting property. The property is that ln k xk equal to 1. Why this is true? Because if you put instead of x equal to xk, all the term will be 1. You consider here xk minus x0 over xk minus x0. Cancel numerator and denominator, and you will get 1 for this fraction. And also the same for all of the other fractions, and finally you will get n 1 that times to each other, and you will get 1. And the other interesting property is that ln k at xi for I not equal to k, you will get ln k xi equal to 0. Why this is true? Because if you put, for example, x equal to, for example, x0, so this term will be 0, and 0 times every things will be 0. This is true for all k I equal to 1, 2, 3, k minus 1, k plus 1, and n. And because I is not equal to k, so all of these terms will be 0. Now, if you consider L, for example, 6, 3x for 7 points, it will be a polynomial of degree 6. Okay, that launch all the nodal points at the xi and 0, and launch x3 at 1. Okay, this is the in fact the graph of L6 3 of x for 7 nodal points. Now we combine the Lagrange polynomial with the values of function f at nodal point x0, x1, x2, and so on, and we define the Lagrange interpolating polynomial to this form: p of x equal to sum k from 0 to n f of xk times ln k x. If we extend this sigma, you will get f of x0 times ln 0 x plus f of xn times ln n x. Okay, we claim that p of xi equal to f of xi. This is true because of the previous property that I told about it. If you, for example, put x equal to xi, so you will get p of xi here. You will have all ln and k at xi equal to 0 except lni at xi, which is 1. So p of xi will be f of xi. Let me a little more explanation here. Consider p of x equal to f of x0 ln0 x, it's not x0, it will be x ln0 at x plus f of no, it should be x0, I'm right, x1 ln 1 x1, okay, and we continue f of x, for example k ln k x x, it should be x, it should be x, not x1, x, this one x, this one should be x, xk, it's true, and this one should be x, and it continue until we get fx n ln n x. Now consider p of x, for example xi, so we get f of x0 ln 0 xi plus f of x1 ln 1 xi, okay, and if we continue somewhere we will get f of xi ln and I xi, and finally we will get f of xn ln I x ln n x I. Now note that here this value is b0, also this value is 0 by the property of ln k, and this value is 1 and the other values are 0. So just remains f of xi, and this is true. This is true. Okay? So this is the Lagrange polynomial. This polynomial is unique, and also this polynomial passing through the points xi f of xi. So in fact p of x interpolate n plus 1 nodal point x0 y0 to xn yn. Okay, this is the concept of the Lagrange polynomial. Now let me show you a very simple example about the linear Lagrange interpolating polynomial. Suppose that we have 2 points, 2, 4 and 5, 1. So let me write it in this form: xi, yi, 2, 4, 5, 1. The aim is to find a linear polynomial that passed through these 2 points. First of all, we have to find L0 of x. If you want to find L0 of x, you have to compute x minus x1, so it will be x minus 5 over x2, x0 minus x1, 2 minus 5. So it will be minus 1 over 3 times x minus 5. And for L1, you have to find x minus x0, it means x minus 1, over x1 minus x0, which will be 5 minus 2. So it will be 1 over 3x minus 2. Now, if you want to find p of x, you have to find f of x0, L0 of x, plus f of x1, L1 of x. Okay, so f of x0 is 4. So you have to find L for L0 of x, and this is f of x1 plus L1 of x. So you have to compute 4 times, consider that this is L0 and this is y0. Okay, it means f of x0. This is L1 of x and this is y1. So you will get minus 4 over 3x plus 20 over 3 plus 1/3 x minus 2/3, and it's equal to minus x plus 6. Okay, so I get p of x equal to 6 minus x. Now you consider p of 2, it will be 6 minus 2 equal to 4. It works. And consider p of 5, it will be 6 minus 5 equal to 1, and also this one works. It means that p of x passes through 2, 4, 5, 1, and in fact p of x, this p of x, this is p of x, interpolate these nodal points. This is very simple problem, and you have, and if you consider the graph of the line, you will get a line like this, passes through 2, 4, 5, 1, and this is the line minus x plus 6. Okay, now let me give you another example. We have 3 points. Let me write in this form. Maybe it looks a little better. yi, and we know that this is f of xi. x0 equal to 2, x1 equal to 275, and x2 is 4. And you consider f of x as a function 1 over x. 1 over x. So for x0 equal to 2, we will get f of 2 equal to 1 over 2. For this one, we will get 1 over 2.75. We have to compute it. I don't know how much is it. 275 and 1 over 4. Okay, the aim is to find a polynomial of degree. Look at here. When we have 3 points, 3 nodal points, the polynomial should be of degree of order 2. Okay, so we want to find a interpolating polynomial of degree 2 such that passes through these 3 points. Okay, so we have to find L0, L1, and L2. Okay, so let me write a little computation here. Change it to black, and let me write. Look at here, L0 of x should be x minus x1 times x minus x2 over x0 minus x1 times x0 minus x2. Here you have to consider x minus. Look at here, this is x1, okay? This is x0 and this is x2. So we will get x minus x1, x minus 2.75, okay, times x minus x2, x minus 4, over x0, it will be 2 minus 2.75 times 2 minus 2, 2 minus 4. Okay, 2 minus 4. Exactly something like this. I think this is not correct. This should be 75. Okay, so consider here x minus 2.75, x minus 4 over 2 minus 2.75, 2 minus 4, and this is L0. In the same way, we have to find L1 of x. L1 of x should be x minus x0 times x minus x2 over x1 minus x0 times x1 minus x2. Okay, so we will get x minus 2 times x minus 4 over 2.75 minus 2 times 2.75 minus 4. Exactly like this. If we compute the values, you will get this is as L1. And in the same way, you can compute L2. Look at here. L2 of x should be x minus x0 times x minus x1 over x2 minus x0 times x2 minus x1. Okay, so you will get x minus 2 times x minus 2.75 over 4 minus 2 times 4 minus 2.75. Exactly something like this. This should be 75. And if you compute, this is L2 of x. Now, if you want to find in Lagrange polynomial interpolating, you have to construct a P2 of x like this. F of x0, L0 of x plus f of x1 times L1 of x plus f of x2 times L2 of x. That we have computed L0 of x, L1 of x, and L2 of x before, and we have fx1 equal to 1/2. F of x1 is 1 over 2.75, and f of x2 is 1 over 4. Okay? Now, here we have something like this. So if you compute this one, you will get this is as the polynomial interpolating of the nodal points. For test that this polynomial is correct or not, you have to put the nodal point 2, 2.75 and 4 in this polynomial and compute the value, and you have to get the same values that appear here, here, and here. They will be exactly the same. Okay? This is exactly the same. This is a very good example for the Lagrange polynomial. And if you compute, for example, 1 over x, this is 1 over x, and this is our polynomial for 3 points. And you can see that in this area, from here to here, the value of the interpolating polynomial and the exact value are almost same, and they are in fact are very, very close to each other. But in some other parts, for example, some parts that are close to 0, it's very far from each other. Okay, so you have to consider the area, in fact the interval that you consider for the values that you want to compute. Okay, now let me stop this lecture here, and I will continue about the error bound of the Lagrange interpolating polynomial in the next lecture. Please subscribe my channel, and please introduce my channel to your friends. Thank you, and wait for the other lectures.